Hello everybody. Today we are going to look at a strategy that is useful in all of mathematics, Math 4, calculus, and beyond, and that is the strategy of making sign charts. Not sign charts like this, but sign charts like this. So, what are these cool things, and how can they be used? Well, let's do a problem. We've encountered a problem like this in previous sections, like a long time ago, and it was how do you find the domain of the square root of x squared minus 2x minus 3? We know that the domain of a square root function is whatever makes the argument, that is, the thing underneath the root, greater than or equal to 0. So to find the domain, we need to solve the related inequality x squared minus 2x minus 3 greater than or equal to 0. So for now, we're just going to forget about the original problem and just focus on solving this inequality. When you have a quadratic, it's usually good to factor it. And then let's think about what possibilities could happen with these factors that would cause this entire quadratic to be greater than or equal to 0. Now, obviously, if the first factor is positive and the second factor comes out positive, so that might happen if x is something like 4. Then you would have, 5 times 4 minus 3 is 1, which is positive 5. Well, that would be one way to satisfy this inequality greater than or equal to 0. But couldn't it also be that one factor is negative and the other factor is also negative? So that would be if, say, x is equal to negative 4. Then you do negative 4 plus 1 is negative 3, and negative 4 minus 3 is negative 7. Well, that's positive 21. And so it seems like if we can decide where this quadratic polynomial will have both factors positive or both factors negative, we will be able to solve the inequality and then find the domain of the original function. And just to confirm that this inequality doesn't just have the solution of all real numbers, let's test a number, see if we can find a number where this fails. So maybe something like x equals 1. So we'd have 1 plus 1 is 2, but 1 minus 3 is negative 2, so we would get negative 4. So then in that case, we'd have a positive factor multiplied by a negative factor. And you see what's happening here is that when one is positive and one is negative, we have a failure to satisfy the inequality. So to solve this, we're going to make this thing called a sign chart. A sign chart looks like a number line, but you don't put every single number on it. So you draw out a number line, and then on this number line, you only need to put the values that are the zeros of the polynomial. So x plus 1 has a 0 of x equals negative 1. That's what would make that factor 0. X minus 3 has a 0 of 3. We'll put that over here. You don't need to make your line to scale. You just need to put those tick marks on there. This then divides the number line into 3 segments. And then within each segment, we're going to test a hypothetical check value. If you've been graphing rational functions with me, you probably already use this method, or you've already seen this method for graphing rational functions, and we're using the same idea. We're just using it now to solve something that looks like an inequality. So I'm going to write down the factors that I have again down here, so it's a little bigger. X plus 1 times x minus 3. And then I'm going to pick some hypothetical x's that I could have. So maybe x is negative 3. Well, negative 3 plus 1 would be negative 2. And I'm just going to record a negative here, not negative 2, because I don't care about the value. I care about the sign. And negative 3 minus 3 would be negative 6. I don't care about the value. I just care that that's negative. So I write 2 negative signs. Parentheses are optional here. Let's check a value between 1 and 3. I don't know, maybe 0. 0 would be here. 0 is a nice number to check when you can. 0 plus 1 is 1, that's positive, but 0 minus 3 is minus 3, that's negative. So when I check 0, I'd get a positive factor and a negative factor. When I check above 3, maybe 4, I know we already checked 4, but I'm just showing the sign chart. 4 plus 1 is 5, 4 minus, which is positive, and 4 minus 3 is 1, which is positive. So now I've written down the signs of each factor in each term, and I'm remembering that these factors, positive, negative, are multiplied together. 2 negatives multiplied together make a positive. A positive and a negative make a negative, and 2 positives make a positive again. These gold net signs are what you need to finally solve the inequality. So, and this is different than rational functions where we now use that information to make the graph. In these, we're going to use the information to solve the inequality. I am looking for where those values are greater than or equal to 0. So on the little sign chart or number line, I'm going to shade or highlight anywhere that I highlighted a positive sign, because that would represent the entire function being greater than or equal to 0. So I'm going to shade that whole region. Actually, I'm going to use purple to shade here. I'm going to shade this whole region on the number line all the way up to -1, and I'm going to include -1 because it was greater than or equal to 0, and I know the function is equal to 0 at -1. And then I also shaded or had a positive sign from 3 to infinity, so I'm going to start at 3 with a closed circle because 3 is included, and then shade off to the right as well. And this is basically a graph of the solution set to the inequality, just put on the sign chart. Then you can go easily from the graph of the solution set that's shaded in to the interval notation as well. Negative infinity up to -1, bracket because it's a closed circle, union because I'm going to have 2 intervals, 3 up to infinity, bracket, and then infinity gets a parentheses. And this is the solution to the inequality. It is also the domain of the original square root, the domain of the square root of x squared minus 2x minus 3. That was the original function, right? The domain of x squared minus 2x minus 3 is that. And which would mean if you were to graph that function, there'd be something off to the left, something off to the right, and nothing in the middle. So we started by solving a domain problem, but that's not the only kind of problem that you can solve with these sign charts. In general, sign charts are useful for solving anything that looks like a polynomial function, x squared minus 2x minus 3, is greater than or equal to, or less than or equal to, right? Could be the other direction, some number. Although we eventually usually want that number to be 0. And anytime you're in the middle of a problem and you find yourself wanting to solve a polynomial inequality, you're gonna want to make a sign chart. Here are the 5 steps for making a sign chart, and we just went through them, but just to recap. 1, you do need to get 0 on one side. 2, you factor everything fully. We did that before. You make a number line with all of the boundary points. Then you test values between the boundary points and write down the sign of each factor. Compute the net sign in each region. Then finally, you shade on your sign chart the intervals that satisfy the original inequality, whether it was greater than or equal to, or less than or equal to, or strictly less than, whatever it was, and express your solution in whatever notation the problem's asking for. Probably interval notation, but it could vary, depending on the problem. And a couple little extra notes up here before we do the problem. A boundary point. A boundary point is any x value where the function could change sign from positive to negative, and there's 2 main types of boundary points. Real zeros, or x-intercepts, which are what you have in polynomials, right? That you factor, you find the real zeros. Those are the points you put on that number line to test in between. If you have a rational function, you also put vertical asymptotes. We won't be covering that in this video, just putting that out there. If you find yourself doing a rational inequality, include the asymptotes, but not any holes. And if you want to know why, just ask me in person when we see each other next. And then finally, one important note is when you're expressing your solution, be very mindful of the direction of the sign, greater than or less than, because that will affect your answer, of course, to the inequality. And please, please, please pay attention to whether the 0 should be included or not. That also will drastically affect your answer because it will affect whether you use parentheses or brackets. And of course, those matter. So we're going to be mindful of all those things, and let's do another problem. All right, we're going to solve x cubed minus x squared minus 9x plus 3 equals -6. And the first move is that we need to get a 0 on the right side of this inequality. I can't do anything, including factoring, until I get that 0. So to move that 6 over, we're going to add 6 to both sides and rewrite. All right, one thing I note is that I am looking for less than or equal to 0 here. That's the less than or equal sign. So the solutions to the inequality are going to be everywhere where I had a minus in the sign chart as the net sign all the way at the very end, or equal to 0. Let's go ahead and factor. So this is a cubic with 4 terms, so it feels like factoring by grouping will be pretty nice. So I can group these two together. I'm going to put that minus 9x plus 9 in its own parentheses, and then the next grouping step, we group out an x squared, and that gives us an x minus 1, and then plus, and here I'll group out a negative 9, leaving me with x minus 1. And then, so then the x minus 1 is a common factor, so I'll group that out, and we get x squared minus 9, x minus 1, and then we'll factor this into x plus 3, x minus 3, x minus 1, and then I'll remember that I'm trying to solve the inequality less than or equal to 0. Pretty much ready to make the sign chart. I'll just sketch a little number line here, and this one I'm not going to worry too much about being to scale. I'll put negative 3 for this 0, I'll put 1 for this 0, and I'll put positive 3 for that 0. And again, doesn't matter whether or not it's to scale, totally irrelevant. I'm going to check values in these 4 regions. So I need to check 4 hypothetical values, and I'm going to check the sign of each factor as we go. So hypothetically, let's test maybe negative 4 as our hypothetical value. Negative 4 plus 3 would be negative, minus 3 would be negative, and negative 4 minus 1 would stay negative. 3 negatives make a net negative. Let's test hypothetically between negative 3 and 1. How about 0? 0 is a great number to test, when you can. 0 plus 3 is a positive, minus 3 is a negative, and 0 minus 1 is a negative. Positive and 2 negatives make a positive. Let's test 2 as our hypothetical value. 2 plus 3 would be positive. 2 minus 3 would be negative. 2 minus 1 would be positive. Positive minus plus is a net minus. And for 3, so let's hypothetically maybe check 4. 4 plus 3 is positive, 4 minus 3 is positive, and 4 minus 1 is positive. So 3 positives would make a positive. All right, so this is the net sign. Now let's remember the inequality we're trying to solve. We need to solve when those factors, multiplied all 3 of them together, create a final thing that's less than or equal to 0 and shade that in. So that will be anywhere that I had a minus on the number line. So that would be the left branch all the way up to negative 3, including because it was less than or equal to, and then also from 1 all the way up to 3. So I have an infinite interval to the left and also a little finite interval from 1 to 3 in the middle. And the other parts where it was positive, that would be where the graph is above the x-axis, not below. We don't include those in our solution set. So the solution set would write as negative infinity up to negative 3 with a bracket, union, bracket, 1 up to 3 with a bracket. And those brackets are all because we had closed circles there. So that would be the solution to the inequality x cubed minus x squared minus 9x plus 3 is less than or equal to negative 6 once we solve everything out. I also want to look at a strategy with this problem that I call an expanded sign chart. It's just a different way for this sign chart to look that might be useful if you have like a lot of factors. And so that's what this would look like, and I'll do it over here. So we still start by making a sort of number line. And we start by putting all the boundary values on there. So negative 3, positive 1, and positive 3. But instead of just calling this a number line, we sort of make it into a t-chart. And then down the side of the t-chart, you put each of the factors. I like to put them in order of increasing zeros. So then x plus 3, x minus 1, and x minus 3, like this. And then on the bottom, I'll write a line underneath where I write the total sign. And then instead of thinking about the function at every test value, I'm going to think about the sign of each factor between every test value. So x plus 3 itself, just x plus 3, would be negative to the left of negative 3, because anything less than negative 3 plus 3 is still negative. But as soon as you jump to the right of negative 3, like, 0 or negative 2 plus 3 has got to be positive, then that factor will turn positive. And as you plug in more positive numbers and then add 3 to them, that factor will always remain positive. So you can kind of break down just the behavior of what's happening to that one factor in isolation, and then we'll multiply them all together at the end. X minus 1, well, something less than negative 3 minus 1 is going to stay negative, and then all the way up to 1, like say, 0.5 minus 1, still negative. So in that whole region, I would write a negative for just the factor x minus 1. As soon as you go past 1, like 1.5 minus 1, now you're positive. So positive here. And something bigger than that, like 5 minus 1, is definitely positive. And then x minus 3, well, something, negative minus 3 is still negative. 1 minus 3 still negative. 2 minus 3, 2.5 minus 3 is still negative, but as soon as you jump past 3, over to 3.5 minus 3, now that factor turns positive. So by doing the expanded sign chart, you can see where each factor flips more often or more commonly, and then you're going to multiply like down each row. 3 negatives multiplied down each row gives you a net sign of negative. 2 negatives and a positive going down each row gives you a net sign of positive. 2 positives and a negative gives you a net negative, but 3 positives gives you that net positive. And then we were shading the net negatives in our answer, so you would, again, just like before, shade where everything was net negative and express your answer. It's the same problem, so it has the same answer as before. This is just a way to make that expanded sign chart. If you have a bunch of factors, it can be really nice as a tool. It takes more time, so if you're trying to be quick, you can probably do the smaller version of the sign chart with like 3 factors. It's not so bad. All right, one last problem for this video. It's a little more complicated, but it's already factored for us, which is really nice. One thing to watch out for is that this is a strict inequality, greater than but not equal to 0. So that's going to affect the answer and like the type of brackets I use. Just whenever you see that, make a mental note. Also, I notice a tricky negative out front that we're going to have to take care of. And because there's like a negative out front and a bunch of factors here, this feels like a chance to use that extended, longer sign chart, and that's what I'm going to do here. So it's already factored. Let me put in the different boundary values. Let's think about what they are. First, for x plus 3, that's a 0 of x equals negative 3. When you have a factor of x, that's a 0 of x equals 0. And when you have a factor of x minus 4, that's a 0 of x equals 4. So those are the 3 boundary values you need to put on the chart. Negative 3, 0, and 4. Now let's go down the side. Now, negative 5 here is a factor, so I'm going to include it, even though it's not something with an x, because it is going to contribute a negative to the sign of the equation. So I'm going to include the negative 5 there. Then I'm going to include x plus 3, and you could write it as x plus 3 squared, or you could do what I'm going to do and just write it as x plus 3 twice. X plus 3, x plus 3. It does matter that it's squared. Then I'll write a factor of x, and I'll write the factor of x minus 4. And then on the bottom, we can write just an f of x to say this is going to be like the net sign. Now let's go across. Well, negative 5 is the easiest. It contributes a negative in every box in the table. X plus 3 contributes a negative to the left of negative 3, but as soon as you jump over, you're adding 3 to something like 2.5, so that's going to contribute a positive to the rest of the table. And x plus 3 again will contribute the same thing again. Positive, positive, positive. X will contribute a negative to the left of 0 and a positive to the right of 0. And x minus 4 will contribute a negative all the way until you get to the right of 4. And then x minus 4 will contribute a positive. So that's how you fill out the sign chart. Then we'll just go down and count up all the net signs. 5 negatives makes a negative. 3 negatives and 2 positives still makes a negative. A positive and 2 negatives, those 2 negatives will multiply to each other and you'll get a net positive. 3 positives and a negative make a negative. So we have a lot of negativity in this chart. The only really positive values are between 0 and 4. And specifically, since those are the only real positive values, if we shade in that in between, that should be our solution set. I'm going to do it down here. You could also do it up there. But remember that my inequality was greater than strictly 0. So if I was graphing that, I would do an open circle here. And that would mean that the solution is just the interval, open interval, from 0 to 4, not including those endpoints. Just a few other ideas here before we close out the video, mostly about this x plus 3 squared. Notice that the x plus 3 factor that I had twice was mostly always positive. But the one time that it was negative, there were 2 negatives together, and 2 negatives together effectively make a net positive. I didn't actually need this line. I could have just made a line that was x plus 3 quantity squared and put positives all across the row. Because that x plus 3 term with a square on it is never going to contribute a negative to the sign chart. It's always going to be positive. You could even not write it, although I would recommend you write the factor, even if it is always going to contribute a positive. Additionally, if you think about the polynomial graph of this, I don't feel like graphing this today, but if you did, we would notice that this has a multiplicity of 2 here, which we would say makes the graph bounce. Well, what is a bounce? It means the graph didn't change sign. And look at what happened in the sign chart. We were negative, we hit 0, and then stayed negative. That's a bounce. And if you ask, why does a factor of multiplicity 2 or 4 or 6 cause a bounce? I would say the answer is that it doesn't change the sign of the sign chart. Whereas any factors with multiplicity 1, when you cross over that factor, it changes the sign in the sign chart. So we're using these to solve polynomial inequalities, but they actually go back and explain a lot about polynomial graphs as well. I hope you've enjoyed this video. I tried to keep everything short. I don't know if I was successful. Please let me know what questions you have. We're going to close it here, and I'll see you all next time. Thanks very much.